Hey everyone, today I just want to talk about a little problem with gyroscopic precession. So, in this example, we have this axle of length L with a wheel attached to it. This apparatus is just resting on top of this stick here. If we weren't to spin the wheel, common sense tells us that this would just tip over and fall down the stick. However, when we spin this wheel at the end with some speed, little omega, what we find is that there's this very bizarre effect where this apparatus will precess around the pivot point with a speed big omega. I would highly suggest watching a video displaying this motion with a real gyroscope and I guess just be fascinated at how mind-blowing it is. It's a very cool effect. Now, in our second picture here, we have essentially the same thing going on, where this axle is now just at an angle with the horizontal, some random angle phi. But everything else about the picture is the same. The goal of the problem is to compare the angular speeds of precession omega, to determine how phi changes the precession rates. We're going to do this by analyzing both angular momentum and torque. We're going to tackle this through a couple fundamental definitions. Let's go ahead and write out the definition for angular momentum, which is R cross P, along with the definition for torque, which is R cross F, and also dl over dt, the rate of change of angular momentum. Now, the way we're going to tackle this is I'm going to make two columns. One column is going to be observed. So these are going to be conclusions that we derive purely from observation. And then I'll make another column called causation, where we think about what is causing the effects that we see. Alright. Let's start by vectorizing this omega here. The way we do that is with our right hand, we curl our fingers to point in the direction of the omega rotation, and our thumb points out in the direction of the omega vector. Alright, there's task 1 complete. Now, for fixed axis rotation, the angular momentum L will point in the same direction as omega. This isn't always true for rigid body motion, and for that reason, don't just take my word for it, we'll use the definition of angular momentum to show the direction of it. I've drawn out the wheel. This is just the front view. So this is its rotation there. Now at the top of the wheel, therefore, we know that our linear momentum, if it's rotating to the left, its linear momentum is going to point to the left like that. And here's our radius right there. So let's go ahead and use the right hand rule, knowing that L is the cross product between R and P. If we do that, the thumb is R, the pointer is P, our middle finger will point out towards us. And we determine that L points in the same direction as omega. Specifically, this is L, we'll call this LW. Or actually, LD. Let's assume that this is just a disk, so this is referring to L disk. I decided against LW because that's confusing with omega. What's a W, what's omega? I don't want to have to think about that. Alright. So what we observe is that this LD must be changing directions, right? So for instance, we know that this axle is rotating. So at some point in time in the future, this disk is going to be over here, inevitably. At that point, that means that LD is going to be like that, and there's our omega. That's inevitable because we know that it's perpendicular to the disk. So if the disk is rotating like that, LD is also changing. So we know that's happening. So I'm going to edit my notation. I'm going to call this LD naught, and I'm going to call this LD final. We can use LD, therefore, as a method to track the wheel. So if there's LD over here, then we can conclude that the wheel must be at this position, right? Okay. I'm going to make a diagram with LD naught and LD final, okay? This plane right here, this horizontal plane that the disk is rotating through, that's going to be just set on this plane basically. So this is LD naught. This here is LD final. There's some arc between them that this disk traverses. And this is gone across this angle theta. Now, this length here is delta L, or delta LD. Delta LD is about the arc length, which I'll call S, is about S. We can write S as LD naught times the angle it traverses theta. The smaller that this angle gets, right? If we have a really small angle, this arc length and the delta LD get closer and closer and closer together. So for an infinitesimally small change in length, we'll call this DLD, this becomes equal to S. So these terms become equal to each other. Okay? Let's take these terms and divide them both by some change in time. DLD over DT equals LD naught theta over DT. We know that the magnitude of LD naught, or of LD, does not change. So therefore, what is changing is the angle with time. So we can write this as LD naught times our big omega, our precession rate. we've just come up with our observed conclusion. dLd over dt equals LD naught times this big omega. Let's go ahead and make a note that this dl over dt is also known as a torque. So what causes that torque? That's what we observe, but what causes it? I'm going to move this out of the way. Looks like I caught a little bit of my wheel. Yeah, I'm gonna have to just select it like that. There we go. I'll just put this under here. This is our reasoning of how we came up with that first conclusion. All right. So what's the cause? Well, what are the forces that are acting on this system? Well, we have mg pointing down, or the weight, and we have the normal force pointing up on the axle. The normal force provides no torque because it is acting at the location of the pivot point. The weight, however, does provide a torque, which is acting a distance L away from the pivot point. Knowing that torque equals R cross F, so torque equals R cross F. Our R is the length L. Our F is the weight. I'm going to calculate specifically the magnitude of the torque, alright? And I'm going to label the direction. So let's start with the direction. Using the right hand rule, with our thumb being the length L and our pointer being the weight, we end up seeing that the torque acts into the page. I'm going to call this TW. So TW. Interestingly, this TW acts perpendicularly to LD naught, right? As in, it would purely change the direction and not the magnitude of LD naught. So that's where we're getting our torque from. That's what's changing the direction of L, which we said was our tool that we used to track the location of the wheel, which is causing the wheel to rotate through space. Okay? So, from here, we can say that this simplifies to just L times the weight. Again, technically, since this is in the page, you could say that this has like a negative direction into the page. I'm not going to worry about that. We're just going to think about the magnitude here. So this is L times the weight. We know the directions just with the picture and our understanding. All right, now we've got the tools. We've got one torque, which we've just realized is really TW. And we've concluded from observation that is LD naught times this big omega. And we've got our other causation that is caused by gravity. So now we can set these two terms equal to each other. And we determine that LD naught times this big omega equals L times the weight. To solve for our big omega, we get that L times the weight is just divided by L d naught. I'm going to make a remark on this real quick, because it's something that we want to take note of. This angular momentum, or this angular speed, this big omega, is also generating an angular momentum that points upward. I'm going to call this L from that. However, one of our assumptions is that this angular momentum is negligible. So LD is significantly greater than L omega. I just need to make that note for clarity, because that angular momentum does definitely exist. Let's not pretend like LD is the only angular momentum that exists in that entire system. There's a second form of rotation. For this second part, we're going to do the exact same process. I'm going to write out an observed column, and I'm going to write out a causation column. Let's start with the causation column again. Or not again, this time, before we started with the observation. Okay, so this time now we know that the cause is from the weight, right? So this torque from the weight this time is equal to R cross F. So we want this perpendicular distance to our weight, which I'll label R. So that we want R cross our weight. And R is just L cosine phi. So this time, our torque is L cosine phi times omega. Perfect. Right, and again, if you're wondering how we get from this cross product to this algebra, when these two are perfectly perpendicular to each other, then the cross product is the same as just the multiplication, at least in terms of magnitude. And I'm not worrying about direction because we're labeling our directions very clearly in this diagram. Now, our observation, well, if this is our LD in this diagram, right, this torque only edits, which goes into the page, only edits the horizontal component of this LD, right? That has no bearing on the vertical component. So, what we care about, therefore, is the horizontal component. So dl over dt equals omega times LD cosine phi. If we set these terms equal to each other, we get that phi LD cosine phi equals L cosine phi times the weight, and our angles cancel each other out, leaving us with this big omega equals L omega over LD. look at that, we get the exact same answer for both of these angular speeds. Let's keep in mind that LD can be rewritten as I naught times the angular speed of the disk. Right? So that's another way that you can see the equation. But regardless, the angle has no bearing on that precession speed. So with that, I hope you enjoyed that little video, and thanks for watching.